So I think we can start. Yeah, I'll kick it off. Hello and good afternoon, everyone. Thanks for joining the webinar. This is a webinar on an open model for the open synthetic model for the Australian national electricity market. We are excited to release it as part of an activity that we collaborated with University of New South Wales. And after a brief introduction, Georgios and Felipe from University of New South Wales will start the presentation by discussing how the synthetic network model for the real-time EMT compatible model is developed and released, and then I'll be sharing steady-state simulation optimization models, which can be run using a variety of open source software packages. And then at the end, we'll have some Q&A. And yeah, thank you very much. Georgios.
Yep, thanks, Arfad. Thanks for also inviting us to give this presentation. We'll put our slides up and we'll get started. Right. Well, two parts in our presentation. In the first one, I will be talking a bit about, well, of course, our research, our lab, and a bit of the research work that we are doing here at the University of New South Wales. And then I will also talk a bit about the motivation for completing this project and the motivation really for developing an open net model for the NEM, what we call the SNEM 2300. Felipe, from the looks of it, I think you are. Am I? Oh, okay. It's different when I take control over the presentation. So let's get started. This is the work that we have really done here at the University of New South Wales in the real-time digital simulation lab. So in our lab, we actually cover three key research areas, which we find really at the forefront of the things we can do with power electronics and the integration of power electronics in the power system, and also with real-time simulation. So our research streams here, we have split them into what we call power electronics dominated power systems. And that is a stream of work that we actually have 4 or 5 PhD students that are working together with, of course, me and Felipe on this project. We are looking at not only power system modeling, which is one part of the work that supports the main area of research that we are developing, but in generally how we integrate small and large scale renewable energy into the grid, how we integrate battery energy storage systems, and what sort of functions and functionalities and benefits we can get from battery energy storage systems in the NEM and generally in all grids. And most importantly, how do we build these systems to be stable? So we're looking at how we can do especially interactions of power electronics and how we can analyze these systems. We also work on medium voltage DC systems. That's an ARC funded project, and also on power system digital twins. So how can we take these models that Felipe later will give a very detailed explanation of how we developed into something more functional, something that can interact with measurements from the real world, and how we can take them into developing test beds for development of other processes, and also how can we move towards self-adaptation of our models and our digital twins. So this is just a quick shot of our labs. At the top, you can see our real-time simulation laboratory, and at the bottom, the power electronics lab that we run together. In terms of capacity with our real-time simulation laboratory, we do have quite a few of real-time simulators that we try to work with and try to develop models and simulations. That includes simulators from RTDS, Opal RT, Typhoon, and Plexim, so Plex. And we use them for both power system and power electronics real-time simulations and models. And one of the things that we see by putting together our labs is work that can be done not only purely on simulations, but also on hardware in the loop testing. So we have the capacity to do control hardware in the loop, something that allows us to test much larger converters, something that we cannot have the capacity to test in our actual power electronics lab, but also power hardware in the loop for our smaller converters, so residential inverters or something up to a few tens of kilowatts that we can test physically connected between the real-time simulator and also the power amplifiers and the 4-quadrant grid emulators we have in our labs. Now, after a bit of introduction, I'll talk a bit about the motivation, what got us here. Because looking back from the development of benchmark models and the development of synthetic grids that try to replicate simulation, that try to replicate models and try to replicate behaviors of real systems into a simulation environment, the state of where we were, at least a few years ago when we started this project, was an environment that allows us to, of course, design, test, and validate processes for power systems and integration of renewables. But most of them were being made on robust or mesh networks. A lot of the work was coming out of the US, and there was a bit of work out of Europe. But we do find, as I will explain later, that the models and the networks that we get from replicating or trying to use synthetic networks that are based on different networks from what we have here in Australia probably guide us towards wrong conclusions or towards not focusing on issues that we will be facing first, given the nature and the structure of the network we have. And another gap that we identified was that a lot of these models were based in RMS models. So although really good at looking at large-scale models and a lot of the stability issues that we used to face in our power systems, they were not really good at capturing issues with EMT-type simulations and the integration of power electronics into the grid. So we needed different models. We needed more detailed models that were able to capture this. So we see our motivation as two-sided. We see the engineering motivation for developing this kind of projects, and that, again, looks back into the Australian network and looks back into power systems that have these longitudinal characteristics. So we're looking at power systems that have reduced number of interconnections between the different areas, very low short circuit capacities, and there are areas in the Australian grid that have very, very weak grids, and we need to try to understand how renewables or batteries or anything we connect at these areas will behave at short circuit ratios that could go as low as 1, and very low also X over R ratios. So the assumptions that we used to have or the assumptions we would make from the mesh networks are no longer there. But also they're quite sensitive, again, the whole weakness of the grid, into these active and reactive power changes. So how do they affect voltages? How do they affect angles? How do they affect the general behavior of all components that we have connected to a particular part of our network? So we see examples like that, also motivated by Felipe in the Chilean SEN. So again, a very, very long network, and here you can obviously see that. But also the New Zealand grid and, of course, the Australian NEM that have very, very similar characteristics in terms of the length they covered, that slimness and weakness of the grid, and also the characteristics of how weak certain areas in the grid are. And these areas are quite interesting because that's where we end up integrating our renewables. So getting back into the engineering motivation, we're trying to understand how we can integrate power electronics into these weak grids. So we face this issue of not having proper models that can emulate or replicate the characteristics and the things we observe in our Australian system. And also, we're a university, we come from an academic interest because we are trying to put our work out there, we're trying to publish our research, but we always come up with the issue of why do you have this issue? Where do you come across such problems, which are not typically experienced in the meshed networks of the US and Europe, and are certainly experienced in the weaker grids. So in terms of the Australian motivation, for a long, long time, have been using the excellent 14-generator model that came out of the University of Adelaide. But again, it started with an RMS model. It was not designed to deal with integration or very large integration of renewables into the grid. So we get across this limit of, yes, we are coming at conclusions. Yes, we can use certain IEEE models and benchmark openly available systems, but they are not giving us the information or they're not giving us the things we observe into our real network. And to answer this, we actually had an analysis, and that's from a paper that was just published a few weeks ago, where we are trying to look at, from a graph-based theory, to analyze these networks and try to see how different the Australian network is, or the NEM, the synthetic model we developed out of the NEM, compared to these other networks. And here, these figures that I saw in this and the next slide kind of try to give this perspective of when you try to compare the characteristics of the NEM in terms of things that reflect length, the distances between nodes, the number of nodes that we have connected at each node, and so on, we end up with a very, very different network compared to what we have with all the other benchmark models and all the other openly available systems. So you can see the red one being the NEM, how different and how far away from all the other benchmark model you can see this. And again, in a similar metrics here, you can see that the NEM may be similar in certain aspects, but very different in other aspects in the way that we try to model, to simulate, and the conclusions we get out of this network, which eventually got us into this question of, well, we really need to get to do something to find better reflection of what's happening in the NEM in a simulation model, which took us into the development of the SNEM that Felipe will cover from the next slide onwards.
Thank you, Georgios. So yeah, as Georgios was mentioning, the idea here is try to bridge this gap. So we came across with this idea of proposing a new methodology for creating synthetic grids, in particular focusing on longitudinal power systems, but as well as to extend or expand the existing synthetic grids. So we would like to, for example, expand the existing RMS models and move towards EMT modeling as well, and to move towards our other kind of topological structures. So here on the right, we have the main steps that we propose to create this model, which starts with an input network model that is used by the industry. So we can emulate the size and the structure and complexity of modern power systems that are being used to study actual networks. The main difference between other works is that we start with this initial input model, but we remove all the confidential information. So we don't have any sensitive information within the model. And therefore, we can then make it public and share the model with everyone else. So the methodology, as I was mentioning, is suitable for any kind of synthetic grid. So it is suitable for RMS models, but most importantly for EMT type, as well as for real-time simulations. That is one of the key areas that we study here at UNSW and in the lab. So we use this methodology, or we applied this methodology to create the synthetic NEM. And here I'm going to highlight some of the key steps that we took when applying this methodology. So as I mentioned, we started with an initial model based from PSSE provided by AIMO. This original model is a phasor-based model, contains more than 2,400 buses, around 350 machines, and more than 450 user-defined models, which are black boxes to everyone else. So then what we did was to group all these components in the system, all the voltage levels, all in just to identify which are the prevalent models that exist in this network. So we can carry out statistical analysis and see which are the main components that characterize this network. So here on the right in this table, I just summarized the dynamic models existing in this original RMS system, where we can see that more than 70% of all the components in this system corresponds to synchronous generators, which can be associated to thermal units and hydro units as well. And we have around 20% of user-defined models or black boxes, where 6% only represent wind farms, for example. At this stage, in this original model, there is no PV, there is no batteries, just few wind farms, but all the rest is synchronous generators, as well as static power compensators, STATCOMs, and so on. After carrying this clustering or analyzing the prevalent models, what we did was to define the generic model that we would like to use in order to replace all the user-defined models, but trying to maintain the characteristics of all the dynamics components that are there. And here on the right, I'm showing that we went with two main synchronous generator units, for example, one for the thermal units and one for the hydro units. At that date, 2 years ago, these represent the main fuel technologies existing in the NEM. And we also define, for example, the type of transmission line that we would like to use based on some physical characteristics, in particular the wave propagation delay. And depending on these metrics, we define which kind of modeling are we going to use to convert or using these kind of components. As I mentioned, one of the important aspects of this methodology is to create an open model that is available to everyone. So to avoid releasing any sensitive information, what we did was to obfuscate the parameters. So we used the OpenRT's unified database, which we extended to allow this randomization of parameters within certain boundaries and based on our statistical analysis, as well as to put in place some constraints so the values or the physical values of all the parameters of all the components in the system are within actual values that you can find in a real network. So we took this adapted model in PSSE, which doesn't contain any user-defined models already, into this database in the RMS domain, and we carry out all these obfuscation inside this database. Using the same database, though, we converted the model from the RMS domain to the EMT domain because we will like to expand the model that we have in something that can be used and is more appropriate to modern power system and studying different kind of dynamics like the integration of renewables. So in this stage, in the domain conversion, we needed to make some assumptions. One of those is considering a balanced network, as well as some typical values for transmission line reactances and ratios between zero sequence and positive sequence, among other factors that we consider. After the domain conversion, what we did was to check that all the components were operating or were appropriate. So in particular, we check transmission line. For example, the wave propagation velocity must be below the speed of light. This is a physical constraint. We also perform different load flows just to check that everything is working and is optimized. So we obtain at the end a very, very small error here in the load flow. We carry out as well unbalanced faults as well, just to see that the system is stable and remains stable after these faults. These are all credible faults that you can expect to happen in the actual network. Once the model was validated initially, we carry out some adjustment for real-time simulations. So we move even further away. So we transform this RMS model to the EMT, and we try to make it suitable for real-time simulations as well. So in order to reduce the computational load of this model and better allocate some of the resources, we split some of these tasks into smaller subsystems, as shown here in this figure. This adds some parasitic behavior in the system, but allow us to reduce the execution time of the whole system and be closer to a real-time operation. So after completing this, all these steps, we came across with the final NEM model in the EMT domain. And here in this graph, I just show you how the behavior of the system changes during different stages of this process. So in blue, for example, we have the original PSSE model with all the user-defined components. And in red, we have the adapted network. It means the one without any black box. And we can obviously see some differences in the behavior of the system, which makes sense because we remove a lot of dynamic components there. But then when transforming the adapted network into the EMT and final SNEM network, we can see that the behavior of the system group remains quite similar. Okay. So the output model looks like the one that we have here on the left. It has 5 distinctive areas similar to the states here that covers the NEM. And this model is a real-time compatible power system model with more than 2,300 buses, around 200 synchronous generators, and other characteristics. The main differences between the number of components or buses when compared to the original model is that we remove all the offline components, for example, because we didn't care about those, as well as we didn't have enough resources. And if they are all offline, then why do we need to consider those? It is worth mentioning that the network, though, was modeled and based on a summer high load profile, so most of the components were connected at that time. And this output model is suitable, for example, for detailed coordination studies of protection and control schemes to assess the impact of existing or new inverter-based resources, and is also suitable and as part of one of the research areas that we carry out here at UNSW is as a test bed for the development of digital twins. So in order just to highlight here the main properties of this model when compared to the original model, again, when considering these two as a graph, we can see that only small variation exists in the properties of the topology of the network, meaning that the resulting model actually behaves or represent a longitudinal power system such as the NEM. And here, for example, I just highlight the maximum span that we can see in this network, which is around 4,000 kilometers long. And as I mentioned, this model can be expanded because the original model didn't have many renewables. We, at the beginning, only converted the main topology, synchronous generator. We left behind some of the inverter-based resources, but that doesn't impede us to continue expanding the model and making it larger and more accurate. So, for example, in this case, we included some wind farms, some PMUs to test, for example, or showcase that the system can be used to assess the renewable integration and analyze what-if scenarios and see, for example, if there is any loss of synchronism in the system after applying some faults or after some perturbations. And as I was mentioning as well, we can use this model as a digital twin or as a platform to test digital twin services. And we can use this model in different platforms to see how the exchange of variables or parameters, or how we can update our digital twin, for example, based on an actual network, may work and test all the services that we can provide. But there is always a but. In this case, we call this the real-time part of the NEM. As we mentioned, this model was developed for a real-time simulator platform, in particular HyperSim, even though we made all the data available to the public. And in particular for this platform, we have 7 licensed cores. And when we run a simulation with a time step of 50 microseconds of this whole model, 10 seconds of simulation takes 7.5 minutes. Okay, and if we keep these characteristics, it means that we will require like around 400 cores to run it in real time. Okay, so this is one of the other challenges of real-time simulations for very large models. You are constrained to the hardware that you have, but that doesn't impede you to use the model in offline and get simulation results as it were an offline software such as a PSCAD, for example. So as a summary conclusion here, we can mention that synthetic networks are used by the researchers, by the industry to test, design, and validate any proposed implementation, analyze, and study future power systems. And we have developed this methodology, and we have applied such methodology to create the first of its kind synthetic grid, a longitudinal power system, the NEM, which is based on the national electricity market here in Australia. And as I have highlighted already, all this information is publicly available and actually has been used already by some research institutes like we are going to see now with Ramat. Thank you. Ramat, all yours.
Yes, thank you very much. I had to mention at the beginning that if anyone has any questions, we can put it in Q&A, but it's never too late before we finish, and we can come back to the questions at the end of the presentation. And yeah, so let me start sharing my screen and hope you can see the screen. Yes. Yeah, so thanks, Georgios. Thanks, Felipe, for the presentation. It was really appreciated. So here in the CSRO, we've been working with power system models and optimization tools, and we saw this great model in real time. And so there's an opportunity to add some features to be outreach to more people who use even the steady state tools. I first need to thank some colleagues and former colleagues like Frederick Geth, Golan Moyatin, Hakan Erkan, and Matthew Amos for helping through the conversion process and some proof of concept studies that I'm going to show after this slide. So we saw this synthetic model, and we added a few features, and such as, well, first of all, we reduced the network from 2,000 plus 2,300 buses to 2,000 buses, so that the steady state and optimization models could converge reliably. And we added line and transformer thermal limits for optimization purposes, and generator fuel type categories, and some cost data based on AMO publicly available data sets. Then we added the HVDC lines that are in Australia, basically the 3 main HVDC lines. And as part of a proof of concept study, we added some candidate lines for transmission expansion planning, and the data are all available. So this model is AC feasible, which is a good thing, and we can see how the reactive power is also flowing in the network. And the data is also, this data is also publicly available, and the report is also available on arXiv. I just want to show where you can find the data. So there is a public repository, GitHub repository on CSIRO GitHub page, and we call it Synthetic Network 2000 bus. It has fewer buses, and there are some .m files, which are math power files, which I'll explain, that are basically the main data files. And I have also provided some scripts and some time series data, which I'll show what they are in the next slides. And basically, you can click on the green button over there up the top and download the whole repository and be able to use it. So the data format is mainly math-powered based data format, which is established in research, and a whole variety of open scientific simulation optimization tools can read it. But so mostly there are some extensions in those math power files that are compatible with powermodels.jl, which is a Julia based module, which is developed by USDOE Los Alamos National Lab, and some other open source tools that can use the same data, like powermodels.jl, powermodel ACDC security constraints, and the ACDC security constraints. Also on top of power models, power simulations.jl, which is developed by US National Renewable Energy Lab, is also developed that requires some additional data, which some generational load branch models for unit commitment and economic dispatch simulations, but you can add them. So they have some types and models that you can use them if you prefer to run different scenarios apart from the models that are already given. So I'm going to show a few proof of concept studies that basically the idea is we saw this real-time, like this network model with real-time data, and we've converted to steady state, and we want to see like it has a lot of opportunity that it can use. One of them is, first of all, you can run AC and basically hybrid AC-DC optimal power flow, and with nonlinear and with relaxations. Sorry. And then we can run unit commitment and economic dispatch studies. We have developed security constraints optimal power flow for the hybrid network, and also conducted some transmission network expansion planning activities that I'll showcase here. So the first case is you have the steady state model, and you want to see how, well, basically get the quality and runtime results of the power flow formulations. So on the left, you see the four main network data that we have. So the whole NEM is, that we call it as NEM 2000.m, which has two subnetworks, which are mainland and Tasmania, and they are disconnected in the AC network. But then again, we connected them through AC/DC by adding the DC line of the battling the AC line, basically, and other DC lines also available in this SNEM 2000 AC/DC. And we tested three formulations: nonlinear, second order cone, and DC formulations for each of them, and got the objective values, and basically determined the gap between different formulations, which are interestingly like they present an interesting test for the relaxation, and how it is not, well, it provides a lot of opportunity in terms of time, but you need more work in terms of improving the formulation and basically minimizing the gap in the if you want to make it closer to the reality. And so for the whole NEM and also the whole NEM with AC/DC, you will have a similar gap, basically. And the runtimes are also representative of the nonlinear second-order Conan DC formulations. And of course, you lose much, but you gain a lot of runtime opportunity. So this is one of the showcases. And as I said, the scripts are available on the repository. The next study is a unit commitment study from Power Simulations.jl that uses High's solver, which is open source. I forgot to say previous one uses IPOP solver, which is also open source. So we use this solver to run a unit commitment study for a day. I think it's about with half an hour resolution, and you can get the fuels and how they are dispatched or committed, basically, and the marginal prices. And you'll also be able to get all the thermal power, renewable power, and hydropower commitment from this study. Similarly, you can run economic dispatch studies with the high solver. We ran it here for 1 hour, and these are the fuels, and it's a midnight. There's basically only thermal power, and I could have shown the renewable power as well, but that's the idea. You can run the simulations and get the outputs and basically manipulate the time series data and run it. And also we are in the process of running a sequential unit commitment and economic dispatch studies. I couldn't get ready for this presentation. Hopefully we'll be on the repository soon. Then the next study is security constrained optimal power flow, which is for the hybrid network with HVDC lines. We use the IPOP solver as a showcase. We show 3 contingencies if a generator fails, if a branch fails, or if a converter station fails. So and the top figures, top 3, they are branch apparent power flows, line loadings, basically. And the second, the middle row, is the generator active power. And the bottom row are the voltage magnitudes throughout the network, in per unit, of course. So we see with the contingencies, you have a lot of violations. And in the branch flow and in the generator, basically, these are the slack generators in the 2 sub-networks. And also the voltage magnitudes will exceed the thresholds. And when we run a preventive security constraint optimal power flow, we can manage the voltage magnitudes, branch flows, and generator dispatch and set point to be contained within their limits. Then the last study that I'm going to show is a transmission network expansion planning activity. For this, we have some time series data on the repository, which are basically adapted from ISP 2024 state change scenario. And it has been averaged for the states, basically both, PV, wind, and demand. That this is just for 1 day, just a typical time series data for each of the states. So we use these data. We run power flow for a whole year and basically determine some weak nodes in the grid in terms of with sensitivity analysis, and identify some candidate branches for expansion planning studies. We use Gurobi solver for this one because it has but it can be as well run with some open source solver like RPOpt and Juniper. Then the next step, we run the optimal power flow for 3 consecutive days with half-hour resolutions. And again, with Gurobi solver, and for each branch, we assigned a binary decision variable indicating if this is built or not, this branch is going to be constructed or not. And out of the 9, 2 of them are recommended to be built within those 3 days. That's the caveat here. If you consider more days, definitely you'll have different or varying results. But yeah, out of the 9 and for 3 days with half-hour resolution, this was the outcome. And this is just the flows of power transfer across the candidate lines that you could use and as a benchmark for basically sizing them as well. Yes, so in conclusion, again, for this work, I had to identify, again, say that the synthetic model is not an exact replica of the actual NEM, as other presenters were also saying, but it's a lot of similarities and good features, but there's always room for improvement, as we have included some HVDC lines, for example. The next step that we are hoping to release is to include some detailed load and generation profiles, basically adapting the ISP inputs to this model, and reiterating that the objective of this open data is to provide some consistent network, a consistent network model for different power system studies. And we hope to encourage researchers to further the power system research and basically to develop tools and algorithms for a complex network such as this synthetic network, which is a NEM level system. Thank you very much. That concludes my talk. I'm happy to take questions. We are happy, I think, to take questions and read the Q&A. Let's see if I can. So first question, I'll read it, and I think it's we can take it. How available is the NEM model to play with scenarios of plant closure, new renewable energy farms and batteries, and analysis of dynamic behavior arising? Felipe or Georgios, you can.
Okay, I go. So, as I hinted there during the presentation, the original model or input model that we used didn't contain much of renewable. In general, less batteries in the system. But as Ramat was mentioning at the end of the presentation, the idea is to continue developing these models so they are closer and closer to what we actually have in Australia. So the idea is to continue including, for example, wind farms, batteries with publicly available information. But again, probably we will use kind of generic models in this case, because we don't have access to these black boxes, but we can continue improving the level of details that we have, and therefore analyze different kind of dynamic behaviors that we will find in the network. But again, the dynamic behavior that we will see won't match exactly the one that you will see on the actual NEM, because, okay, this is, again, a synthetic network, and probably all these dynamic models that we are going to include are going to be generic as well.
Yes, thank you very much. There are more questions in the chat actually than the Q&A. So I'll read from that. I just noticed them. Does the simulated model include the DC link between the mainland and Tasmania? Yes, as I mentioned. The steady state one does, not the real-time simulation. Real-time EMT1, and does the DC link have any effect on the result? It is considered, yes, indeed, the cost will be higher, the security constraint, all the optimization power models require different tools and with different complexities, of course, and yeah, definitely has a big impact. Do you consider to benchmark short circuit MVA fault level in the SNEM 2000 network? So it's not in the short-term plan of mine, I would say, but certainly an interesting aspect. But we need to, yeah, just have a look at it. Happy to hear more feedback on this as well. And Georgios has replied already. Noticed. Do you think this can have some effect? Yeah, that's all good. I think, yeah, Georgios has kindly provided some feedback there. The other questions? Just trying to see.
Sorel makes a very good case about cross-referencing with publicly available data, but
Yes.
having a look at the map and the diagrams that are linked in that file. Yeah, I think it's a question. I think with all this model development, it's a question of like resources that are available, and that includes computational resources in what can we do to once we run this model, but also human resources, as in going through all the parameters of the models and trying to cross-reference one to one to one to one to one to one all the parameters versus having a semi-automated, if you want, because in the end, going back to how Felipe described the methodology for converting this, it at some point requires a bit of semi-automation because it's impossible to get, or it's actually quite difficult and quite time-consuming for very few people to do that in a reasonable time constraint. If you have a big team that has a main operational goal, if you want, if you're IMO and you're trying to do that, then I can see the point of trying to go into a lot more details. But I would say for open models or something that works as a starting point to see what more can we do. Yeah, I think that this is a bit too much work to justify getting someone to do it without an outcome. I think if we know why we're doing it, then certainly. But to just embark on an exercise like that for no goal, it's a bit difficult to convince ourselves to do that.
Yes, and I think I want to say again that the whole, even for simulation, and the idea for the open data is basically to encourage research and encourage development of algorithms and tools that can handle these complex networks. Because as much as there are other open data, and I've gone through many of them, there are still interesting aspects to Australian NEM that can be still seen from real time to steady state, and yeah, developing those tools. Yes, just hoping to. Another. We consider comparing the power flow in the conductors with the AMOS data. No, we haven't compared any as far as my response goes, that we haven't compared to any existing or actual interconnected data because there's no one-to-one. And this is, as George and Felipe were saying, so this is developed based on a specific PSSE fault, and at the time there was some generators, let's say, were not scheduled, so that's in a way that's not the exact NEM for different times, but as much as it captures the reality, can run different studies on that. And how did you model the load? You guys want to?
Sure. Yeah. So actually, I was searching for a link, and I will provide that on the chat, we use a dynamic load kind of model for all the loads in the system, because the original from PSSC, it came with different kind of models like constant impedance, constant MVA. But at the end, what we decided was to use the dynamic load, which can represent the behavior, or in the same component represent different behaviors of loads. And I just provided there the link where you can find more of how this load is modeled in the particular SNEM for the EMT model. Yeah.
Yeah. And then I used that load. I was gonna take it away. Then as a base for and then multiply by some factors that we get from, let's say, those time series. So the time series data that there is in CSR repo is basically some multiplication factors to that, to the steady state of those load models that you guys have for future scenarios, basically.
Yeah, that I think that's the main idea, to have this kind of starting point, which is the benchmark model. Then you can expand this model and perform different kind of studies and analysis, like in the future, like you are doing, for example. Or if you are interested on study the dynamic of power system, then you can integrate or develop new models for renewables, batteries, include the HVDC systems, and see how they affect the whole system. At the end, that's the idea, is to generate this model that can be extended, expanded, and anyone can use it.
Yes. Yeah. Absolutely. Thank you. And John is, yeah. How can the data actually, which data actually needs to be, changed, which Georgios provides some feedback.
So regarding the obfuscation of the parameters, that seems like it's causing a lot of questions there.
Yes.
So again, the original model itself is sensitive in general. So only few participants can access the original model. It contains some codes that you may have no idea to which substation, for example, corresponds, unless you work in the industry and have access to these codes, and which we don't. So what we did was to treat most of this information as sensitive, but the voltage levels, which, as Sorel provided the link, actually we considered that link to check, okay, this information is available, so we can actually keep the same voltage levels. Otherwise, we will need to change the voltage levels as well. So on the one hand, what we did was all these user-defined models or black boxes were replaced with these prevalent models that we identify when clustering all the components. And then all the parameters of each of these components were analyzed and then randomized according to the values that we had from the clusters. And I cannot give you further information, otherwise you will kind of go back and get the original values, but that's the idea. We get all these parameters and we modify all the parameters, and that's why we check that the load flow converges, that the simulation runs in after applying fault, for example, just to see if this combination of parameters were okay or not. And we also applied some constraints, obviously, when changing all these parameters and obfuscating the parameters, so they remain within certain boundaries of existing and real parameters that you can find in actual systems.
Can I
Hopefully
talk about, yeah, a bit, Felipe, because you did mention the black boxes, which effectively are non-accessible, and they would be also trying to answer the question in the chat. The moment we And obviously, we do not want to have access to the black boxes because that's for the operational aspect of IMO. But the moment that these black boxes exist, and we're also trying to implement them in real-time simulation, makes things really complicated. It makes it complicated from an IP point of view, as in IMO does have access to this, and they can certainly use a model and develop a model where they can request these black boxes to convert them into real time, but certainly that's not something for us. That's a major differentiation, if you want, between what an open model or a synthetic model can be and what an actual model of the NEM would be. And also, in terms of running these black boxes with real-time simulators, talking with those who are developing the real-time simulators themselves, you'll find that it's quite a challenging point, because the way that the black boxes are wrapped around the black box in order to be obfuscated, to get that to run in real time is actually something that maybe not at the full model yet, or like fully available components. I think both RTDS and OpenRT are working really hard to get compatible version that allows you to get the real-time simulators to work with black boxes. And that makes it an extra step more challenging. As in, the actual model, you would really want to have the black box models because that gives you the real characteristics. But we're not there yet. Even the developers of these products are not there yet. And it's not something that certainly would be openly available for the rest, for the academic part of the work that we're presenting here. So it's a balance of the two, which also leads us towards what can we choose to obfuscate, and are we obfuscating because we also want to substitute things because we don't have access to the information. So it's a balance between what data you have and what you know that you will never have.
Yes, thank you. So what more? Yeah, okay. Question on how do you set parameter values for generic dynamic models for synchronous generators, as user-defined models do not have description of their models?
Okay, yeah, that's a very fair question. And we needed to make some assumptions as well. So you have all these black box models, but you can still open those models and see the definition of the parameters. Well, hopefully, otherwise it will say just parameter 1, parameter 2. For those that has the definition, you can actually see, for example, the value of the reactance, let's say for a synchronous generator. And by checking with typical values of existing synchronous generators, you can place this one in particular into a thermal, for example, unit or a hydro unit. And if that was the case, then we did that match. If we had no idea about that, what we did was to analyze the existing installed capacity in the NEM and try to keep the percentage of thermal and hydro units, which were the two main that we consider in this first development of the model.
Yeah. Great. So we are at time, hoping to see if there's any questions left. But in case any questions left, we're happy. I think you can reach us. And also, yeah, I think we'll share the recording. And yeah, there are reports and papers available, as well as the data sets ourselves. So don't hesitate to reach, and we're always happy. I think I'm talking on behalf of Felipe and Georgios to collaborate and provide feedback on each side and help with the next steps.